Hey Chunk, could you give me a minute? I'm studying for my qual. Oh, no, you don't understand. Do you know what they do to people who don't pass their qual? They make them get a master's. Today we're going to talk about connectedness. Wait, connectedness? We already know what connectedness is. This is connected, this isn't. Ta-da, there you go. You didn't think I'd do the same joke 2 episodes in a row, now do you? Well, I did, because I am out of ideas and... Actually, the pictures do give us a good way to think about connectedness. We can look at a picture and say, this is connected, this isn't. And the actual definition basically reflects this. The idea is that a space can be separated if it can be broken up into 2 globs, which is 2 disjoint, non-empty open sets whose union is all of X. If there's no possible way to cook up such a separation, then we say X is connected. It's also very easy to see that an equivalent way to describe connectedness is to say that the only clopen sets are the empty set and X itself. Neat. As always, when you first get a definition, the very first thing you want to do is get some examples under your belt. And not these mamby-pamby, ooh, la-di-da, look at me, whoop-de-doo, I'm a picture examples, but some... I think I lost my train of thought. So let's show a couple of spaces that aren't connected by building explicit separations. Well, Q had better not be connected, because we visualize Q as a bunch of dense little dots collected in R. And indeed, here's a specific separation. The open interval -infinity to pi intersected with Q, and the open interval pi to infinity intersected with Q. Of course, there's nothing special about pi, any irrational number will do, but those are 2 non-empty, disjoint, open subsets of Q, whose union is Q itself. And always remember we're giving Q the subspace topology inside of R. Here's another example. Our old friend 0, 1 to the n, which is countably many copies of the space 0, 1, each with the discrete topology. Remember that the elements of this space are just infinity tuples where every coordinate is either 0 or 1. Here's a separation. The set of all infinity tuples that begin with 0 and the set of all infinity tuples that begin with 1. Clearly every infinity tuple begins with either 0 or 1, so this disjointly covers 0, 1 to the n, and both these sets are open, because they're the preimages of 0 and 1 under the first projection. Thus, 0, 1 to the n is disconnected. Actually, we can say even more. Let's say that a space is totally disconnected if the only connected subspaces are the singletons. In fact, 0, 1 to the n is totally disconnected, because if you take any 2 different infinity tuples, then they differ in some coordinate I, and so you can put one in the preimage of the ith projection of 0 and the other in the preimage of the ith projection of 1. Thus, any 2 arbitrary points can be separated, so the only way to remain connected is if you're a lone singleton. Finally, an example of an actual connected space, R. We'll show that a separation is impossible. We'll need to borrow a few facts about R. I don't know why I just said borrow. We're not gonna give them back. R is Dedekind complete, which means if you hand me a set that's bounded above, then the supremum exists. And R has the Archimedean property, which means if you hand me any 2 real numbers, then there's a real number between them. Okie dokie. So, let C and D be disjoint, non-empty, open subsets of R. The idea is that this is a tentative separation, but we'll show that C and D cannot cover all of R. Here's the trick. First, pick a point little c in C, and a point little d in D, and just suppose that little c happens to be less than little d. Then we have 2 new sets, C prime, which is C intersected with the interval C to D, and D prime, which is D intersected with the interval C to D. Now, C prime is bounded above, so let X be the supremum of C prime. If we can show X is not in C prime, and X is not in D prime, then X can't be in either C or D, and so C and D don't form a separation of R. So first, could X be in D prime? Well, D prime is open inside of the interval C to D. So there exists a point alpha in the interval C to D, such that the interval alpha to X is contained inside of D prime. But then alpha is a smaller upper bound to C prime than the smallest upper bound X. So there's a contradiction. X can't be in D prime. Okay, Well, could x be in C prime? Well, like before, C prime is open in the interval C to D, so there exists a beta in the interval C to D such that the interval x to beta is contained in C prime. But by the Archimedean property, there's got to be some number z in between x and beta. But that means that x isn't an upper bound to C prime, which is again a contradiction. Thus, x isn't in C prime or D prime, so x isn't in C or D, and thus R isn't separated. R is connected. Ta-da! Let's talk about some results involving connected spaces, and then later we'll cook up an even stronger version of connectedness. So, what theorems would we like to prove? Let's try and show the following. If we take two connected spaces, then their product is also connected. To do this, we're going to need a couple of small results along the way. First, if C and D form a separation of x, and y is a subspace of x which is connected, then either y lives in C or y lives in D. What you'll see when we deal with separations and connectedness is that because the property is defined as a negative, connected means that there is no separation. That means that a lot of proofs are going to work via contradiction. So, suppose to the contrary that y doesn't sit entirely in C or entirely in D. Well, then y intersect C and y intersect D form a separation of y. Check the details yourself, or ask in the comments like always. But we said y had to be connected, thus we reach our contradiction. Okay, there's one result. Second, if y is a connected subspace of x, and you have a collection of connected subspaces y sub alpha, such that y intersect y sub alpha is non-empty for every single alpha, then the union y union with all of the y sub alphas is also connected. Before we even prove it, I want you to note that it's just pretty obvious via this picture. For the proof, now suppose we've got a tentative separation of this space Z, call it C and D. We're calling it tentative because while we assume that C union D is all of Z, and that C and D are disjoint, we're not necessarily assuming that both of them are non-empty. So we'll finish the proof when we show that one of them is empty, so that no separation can exist. So, by theorem 6, y has to live entirely in either C or D, as do each of the y sub alphas. Let's say y lives in C without loss of generality. Now, since all of the y sub alphas non-trivially intersect y, that means every single one of them has to live in C as well. Thus, Z, the union of all of these things, has to live in C too, and thus D is empty, as we wanted to show. Great, 2 results down. Now let's prove our main claim. If x and y are connected, then so is x cross y. This proof is pretty clever. We're going to decompose the space x cross y to take advantage of some of our previous results. First, let's fix some point x naught in x, and consider the function f from y to x naught cross y, defined by sending a point little y to the ordered pair x naught comma y. This is easily seen to be a homeomorphism. So since y is connected, x naught cross y is connected as well. Alternatively, you could just prove a slightly weaker statement that because y is connected and f is continuous, then that means f of y is connected as well. That's actually called the Intermediate Value Theorem, and I can hear some of you calculus students gasping from across time and space.
Wait, that's the Intermediate Value Theorem?
I hear you say.
That's not how we learned it in Cal 1.
Ah, but au contraire, ma chère, c'est la même chose. Your homework is to see why this statement is the same as we give the Cal 1 students, except just a little bit more general, and then prove it. It's not too tricky. Anyways, back to the proof. So we've just seen that x naught cross y is connected. By the very same argument, x cross little y is connected for every single little y. So we have this single vertical connected space, and all of these horizontal connected spaces. They all intersect non-trivially, as you can see along this line, and the product x cross y is the union of all these spaces. Thus, by theorem 7, x cross y is connected, as we wish to show. Neato! Now, of course, by induction, any finite product of connected spaces is connected, but it remains to be seen that the same is true for infinite products of connected spaces. I mean, it's true, but it remains to be seen. Now, let's talk for a minute about a stronger version of connectedness. It's called path connectedness. A space is path connected if there exists a path between every 2 points. Okay, so what's a path? A path from x to y in a space x is just a continuous function p from the interval a, b to x, such that p of a equals x and p of b equals y. The path is really the function itself, but of course you should visualize paths by drawing their images in your space x. So paths visually look exactly like they're supposed to. A quick example to calibrate this definition is to see that Rn is path connected. Here's 2 arbitrary points, and here's the path. We claimed that this was stronger than connectedness, so we really ought to prove that. If a space is path connected, then it is connected. For this theorem, the contrapositive is going to be easier to show. Not connected implies not path connected. That's because if x is not connected, then we have an explicit separation C union D that we can get our hands on. So suppose P from A to B to X is a path. Since AB is connected, P of AB is connected by the Intermediate Value Theorem. Did you do your homework yet? By theorem 6, P of AB lives entirely in C or entirely in D. So there's no way to build a path that connects a point in C to a point in D, and thus X isn't path connected. Okay, but I also claimed that these are genuinely different concepts, path connectedness and connectedness. That means that we should be able to cook up an example that lives somewhere between the two, a space that is connected but not path connected. Enter everyone's favorite such example, the topologist sine curve. Okay, well, not everyone's. There are infinite brooms and leaky tents and other spaces that are pretty cool too. But what is the topologist sine curve? We're going to build it in stages. First, consider the function f from 0 infinity to r, defined by f of x equals sine of 1 over x. We begin by considering the graph of this function as a subset of R2. Let's call this space S. At this stage, S is path connected, so it's connected as well by our last theorem. Now, here's a second homework problem for you. If I hand you a space which is already connected, then adding some or all of its limit points won't change that. The resulting space will still be connected. Thus, we can do the same for S. If we add all of the limit points of S and get the closure of S, then the closure of S is still connected. But what does that look like in our picture? The limit points that we add are going to be everything on this vertical line. Let's call this set Y. The entire picture of the closure of S is the topologist sine curve, sitting inside of R2. To see that the closure of S, which is S union Y, is not path connected, suppose we have a path from 0, 1 to the closure of S that begins in Y. We claim that it has to stay in Y, that there's no way to get onto S. Suppose to the contrary that the path starts in Y, but ends in S. Then there's got to be some moment t0 where we leave the set Y and never return to it. That means that the restriction of P from t0 to 1 going into the closure of S has the first point in Y, but every other point inside of S. We'll deduce a contradiction by cooking up a sequence Sn that converges, but where P of Sn does not converge. And that isn't supposed to happen because P is continuous. So suppose here's the tail end of our path. Maybe our path doubles back for a while and retraces steps sometimes, but we can straighten it out so that that's not the case. Now let's build that sequence. What's the nth term, Sn? Well, pick the peaks of the sine curve, top and bottom moving towards the left. These points are going to be our P of Sns, which don't converge because they bounce back and forth between -1 at the bottom and 1 at the top forever. But because we're moving to the left, the sequence Sn does converge to the starting time of our path, t0. So P didn't keep a convergent sequence convergent. So P can't have been continuous, which is a contradiction because paths are supposed to be continuous. Therefore, the topologist sine curve is connected, but it's not path connected, no path can exist between S and Y. That's a neat example. Hopefully, as we've talked about connectedness, you've had some fun and learned some new stuff. Maybe this experience has even brought us closer together. In fact, you might now say that there's a real connection between us.